So welcome. It's good to see you here on this first day of spring. I'm Jane Vossler, and I want to welcome you on behalf of the Community Senior Center. We're excited to have Kevin here today to talk to us about Rocketry, and I'm going to turn it over to him and let him introduce himself because he knows his story much better than I do. Okay.
Thank you, Jane. So you've got some empty seats out front, so if there's any rocket nerds out there, my wife told me after about 5 years of marriage, she didn't realize how much of a geek I was, you know. I kept it hidden, so I guess it was a covert one. BAR? BAR? Born Again Rocketeer. Ah, that's what I am. I actually am. So I moved up here to Richmond about 5 years ago. I've been in town, had a house here for a good decade now. And when I retired, I was looking for things to do. And one of the things I wanted to do was to get back into rocketry. As a kid, my brothers and my father, we used to launch rockets out in our backyard. And so I went back into rocketry. And when I went to the club and actually attended one of their launches, I found out that the world has changed. The idea of low-power rockets is so old compared to what there is now and available. And so that's what I'm going to talk to you about, to give you a bit of an introduction to rocketry and all. And to start out here, I show you, this is the type of rocket that I would have made when I was young and launching out in the backyard and out into farm fields. This is called a low-power rocket, and all rockets are basically the same in the sense they've got, at the low-power range, they've got a cardboard tube. It's a body tube. It's got a plastic nose cone here. It's got balsa wood fins. So it's basically a very light object, and you put a motor in the back here, and when it gets up the top, it would pop out and deploy a parachute. So this is what we launched, and the way you would do it is you would put a motor in, and let's see here, where did I put my motors? Inside. I'm not going to really load up a motor or anything, but because they do have some rules here. But this is a typical motor. This is an Estes motor that you'd use in a low-power rocket. This thing is made with black powder, and so they compress the black powder into a motor, and you'd place it inside the rocket here in the motor tube, and you would place it on a launch pad, and there's little straws that are actually on the rocket that would slide down the launch pad to help guide it. And so when you put the rocket in there, you put igniter into the base of the motor, and it'll be electronically set off at a distance, a safe distance. So the Estes would require you to be at least 25 feet. Well, our club, we do it at 50 feet. And you'd electronically launch it, and it would start burning at the very base of this. And as it burns, it would build up pressure, and it would shoot off. This rocket here would go a couple hundred miles an hour, between 100 and 200 miles an hour. And it would go up, and it burns for maybe a quarter of a second, you know, of thrust. And then it would coast the rest of the way up to apogee. So that'd be for another, 10 seconds or so. So it's surprising that you would think that burning and pushing the rocket all the way up, but in reality, it's just coasting most of the way. And while it's coasting, this motor has a smoke charge in there, so it's leaving a trail of smoke. So that as it goes up there, it's hard to see. And so it would leave a trail of smoke so that you can actually see where it's going and try to track it that way. And then when it gets close to its apogee, or somewhere around there, it would set off a little charge at the other end of the motor, and it would actually blow out the chute, and the chute would open up, and it would come back by chute. There's other types of recoveries out there on these low power rockets. They've got some that are so light that they can just fall back to earth and they don't damage or hurt anyone. Some of them have streamers. They come down a little bit faster. And then there's some that have actual wings. So these types of low power rockets here come in kits, much like this. And you can build them, use standard either white Elmer's glue or yellow wood glue. And you can actually build these types of kits yourself. They're available in hobby stores around town, around the area. And you can buy the motors as well. So that's what I did as a kid. And then I went off to college and then, 30 some years working for the government down in DC. And then I decided that I wanted to get back into rocketry. So I found a club up here at Champlain Region Model Rocket Club. We've got about 34 members made up of Canadians, people from New York State, New Hampshire, Massachusetts, and Vermont. And we meet the third weekend of every month, depending on weather, up near St. Albans. So we've got a site up there where farmers allowed us to actually launch from his property. And we have about 400 and some acres that we use. And we do launches. I'll show you a little bit of that later. And when I got there, and I watched their first launch, and I found out the world had changed. The idea of having a rocket that's made out of cardboard and balsa wood, a lightweight plastic nose cone, and these type of rockets, you can get up to about 3 pounds, and you're limited. So that's called a lower power rocket. There's another category, it's called a mid-power rocket, which is a little bit bigger versions of these that you can still buy motors, either mail order or possibly some of the stores around here actually having that go up with a bit bigger motors. I should talk about the motors while I'm at it. So this one, where did I put the motor? So this is called a C motor. They come with a letter designation at the beginning. So this is a C. So they start out at A, and each letter doubles in power. So B is double the power of an A, C is double the power of B, and so on and so forth on the way up. And you can stay at mid-power up through G. And then after you hit G, you have to go into the high-powered world. So for high-powered rockets, they have rules, and you need to be tested to verify that you can do this safely, because these rockets are beginning to become very heavy. They're over 3 pounds, about 3¼ pounds minimum. And they also have a lot of rocket fuel in them, and they go very, very high and fast. And so therefore, you need to be going through a certification process to make sure you can handle it safely and buy them. So these other 4 rockets here are actually high-powered rockets. These are all that I've built. And how they differ from a rocket like this that I did as a child is that they are more durable. So they have, they're made out of like fiberglass. So we're going from cardboard to fiberglass. The fins can either be plywood, or in this case is fiberglass. That one's over there is a canvas phenolic. So they impregnate the canvas to make it hard with resin, and or a composite material like this fins over on this one here. And these rockets weigh from, oh wow, they can weigh up to several hundred pounds on the high power range. So for a level 1, their level 1 could be basically any of the black one, the orange one here, and the red one. And by the way, at the end of the show here, or talk, I do have little cards by them so you can see how high they go and all that. Anyways, so they're They start out with more durable material. They have bigger motors. So like I talked about for low power, you have motors like this. And I may pull out some motors here. They go up to, this is probably the lower end of the low power size, because that's as you can see, it's quite a bit bigger in size. Then you get up to the next size. And then eventually you get up into the higher levels of certification. You get into motors that are like this, and they make them even bigger than this. So this is a 75 millimeter diameter motor tube. And I would put the inserts into here. And I've left all the inserts and stuff at home because I don't think they want explosives inside this building. And so that's a 75 millimeter. They go up to, there's next size is 98 millimeters and 150. And I think there's one even higher than that. So these become very powerful motors. And so that's part of why they do the certification process. The other thing is the height, the altitude that these rockets go. They operate basically the same as the low power ones, but when they get up to the high altitudes, you have a problem. So like this rocket here could go up about 6,000 feet, okay? And it'll travel about 750 miles an hour when it's going up. And it'll burn like that for a few seconds, and then it coasts the rest of the way up. But when you get that high up in the air, and it opens up a parachute, and this wind, of course, is blowing a lot harder up there than it is down on the ground, you could end up with it drifting several miles away. And that means you're going to lose the rocket, and that becomes very expensive. So how these rockets differ than a normal low power rocket is that they have an electronic bay in the middle, and it has a computer in there, a flight computer. And a flight computer, I could show them to you probably easier later, but they're just little cards like this here. Most of them that I have, I actually make. I actually solder the pieces together. But these flight computers keep track of the rocket. One, it's looking for first the apogee. In other words, when it gets up to its maximum altitude, it then decides that it's up as high as it's going very slow. It then separates first part to put out a small chute to allow the rocket to fall back to the earth in a controlled fashion. And it does that so that it's not drifting very far. So it's falling back rather rapidly. And then when it gets close to the ground, a few hundred feet for a rocket this size, it then senses it's reached that altitude that I've set, which is like 400 feet, and then it would blow the nose cone off and put out a real big chute to slow it way down, try to get down to about 20 feet. So this thing's moving it's falling about 30 miles an hour under the drogue, and then when you get to the bottom one here, you're dropping down to, I know it's about 20 feet per second. I can't remember what the conversion that is to actual the actual speed in miles per hour. But let's look at my bigger rocket here. I'll take this one here apart. So this one here has this one here can take that big engine that you see in there. And so you put the engine in there. We've got retainers that allow us to physically hold the motors inside, which is one of the requirements because it screws more than I thought. But as you put the motor in there and screw the cap back on, you would then put it on a launching rod. And so to hold it, the other ones, the low power ones, use little straws. These here actually have rail buttons. These are little plastic buttons that fit inside of a extruded aluminum. I don't know if you've ever seen an extruded aluminum, but I didn't bring in any launch rods, rail systems here to launch with. But it slides down it, and these rails are between 8 to 16 feet tall, depending upon how much guidance we need. So you put the rocket in there, and once you get it installed, you then turn on the electronics. And this one here would be done by pulling out a safety pin like this, and then that would activate the electronics. And you pull it out now because once it's on the launching system, because that activates the computer, which energizes the charges that are inside the rocket. And once that's all charged, you listen for beeps to make sure everything's still hooked up properly, because who knows what's happened between the time you assembled it at your table and you brought it out to the launch pad. But the rockets will signal back, usually through audio tones. One of my flight computers I build use Wi-Fi, and you can actually pull up a page and you can see if the drogue chute and the main chute are both powered up properly. There's connectivity all the way through. So you pull this out, and that way the rocket is looking for a launch at that point. And then you install your igniter in the bottom, electronic igniter. You have to put it all the way up into the motor. And these motors are different than the black powder motors that I showed you for low power. They use APCP, which is a compound that's the same as what is used by the space shuttle, and it's solid propellant motors. It's also used by a lot of the missile systems that are being used in the Ukraine war. As because of that, we're finding a shortage of APCP, so it's hard to buy motors these days because of the war effort is consuming all the power or all the APC that's out there. And so you put an actual igniter up into the motor, and the small lower power motors would burn from the bottom and work their way up. The bigger motors on these high-powered rockets actually burn from the top. They ignite it at the top, and then they ignite the entire tube, the full length, and then they burn outward. So it's totally a different way that they work. But they generate a lot of pressure, and that pressure comes shooting out the nozzle in the bottom, which gives you the forward motion up. So you put the igniter in, you got your flight computer working, and based upon the size of the motor determines how far back you have to be, because we're talking about safety here. So for a rocket of this size here, it could be between 300 to 500 feet away from you, because you don't want it, if something blows up or something, you want to be a long ways away. So you, the person who's running the launch will do a normal countdown. They view the area to make sure that the sky is clear. There's no planes. Up in St. Albans, there's an airport nearby. It's like Franklin County Airport, and they have a bunch of training schools up there that for people wanting to learn how to fly. For some reason, they will see a bunch of us standing out in the middle of a field, and they start circling overhead. And that sort of shuts down our launch until we can get them to move out of the area. And by the way, because of these rockets, because they go so high and everything, we have to work with the FAA to close the airspace over the launch field. So before every launch, a couple days before, we contact the FAA, and then we put out a notice to basically the pilots, NOTAM, and basically tell them that here's where our launch site is, this area a mile around our launch site, up to 10,000 feet, which is the waiver that we have that allows us to launch that height. The airspace is closed down, and so if those planes get in our area, we have to wait until they get done. We can call the air traffic controller, but they usually say that people aren't listening, that they turned off their radio and are just joyriding up there, and so we have to wait till they're out of the area. But anyways, so we got this on the launch pad, and we've got the computer activated, got the igniter in there. The launch control officer will check to see if we got continuity to the igniter. So verify that that's all working. They check the safety for the airspace. They make sure nobody's around the pads, everybody's back the proper distance. And they would do a countdown for high power. You got to start at 5 and work your way down. And then they hit the launch. And if you saw any of the video at the beginning, it showed the actual launch of these types of rockets. That the rocket will take off under some type of motors. They can be very, very, very fast. Some of them will move fast, but not as fast. Like if you're not watching up at the time that you launch, you will miss the entire rocket. They actually go up that fast. But they go up, and the first thing the computer does is it registers whether or not you've achieved a valid launch. So it's looking for altitude change, so it's looking at the pressure sensors on it. It's also looking at the accelerometers, so it wants to see that you've gotten up 100 or so feet, and then it activates the charges. The reason is that if I have it on the pad and the wind's blowing and it's going through these little vent holes here where the eBay is, it could it could make the computer think that it's actually had a launch because it sees a pressure changing. And you don't want that to happen, so it has multiple features to detect whether it's actually a successful launch or not. And if it is successful, it lets it go all the way up to the apogee where it does the first charge, which is to jettison the drogue chute. But if for some reason the rocket isn't going right, like say one of the fins breaks off and it starts to spin out of control, the flight computers have safety measures as well. So these safety measures will detect anomalous state, and when it has anomalous state, it'll blow all charges. So it'll blow both the drogue chute and the main chute at the same time. The idea is trying to stop everything super fast and bring the rocket back down, even though the engine may still be going. So that's a safety feature as well. So it gets up to the apogee here, and the first part here is it blows off this top part here. And out of here comes the drogue chute, which I'll just pull it up here. So one thing is we have Kevlar, a Kevlar cord here that actually keeps these pieces all tied together. And you have a blanket here that's made of a fire retardant material that protects the chute. The chute is nylon, and it will melt under the heat of the charges. And it opens up the first chute. This one here is about this is 28-inch chute. So this is the first chute, which drops it back to the ground about under 50 feet per second is the goal, okay? And I told you about how the charges actually separate the pieces. Well, this one here has 2 charge wells. And so I put black powder in each of these charge wells. There's a little igniter inside of each of these. And there's actually 2 flight computers in here because this one's a heavier rocket. I have a redundant system. So I have totally redundant batteries, totally redundant flight computers. So in other words, 2 flight computers, 2 different paths of wires, and charges as well. And so when it sees apogee, it blows one of these charges. It pressurizes this cabin, this body tube here. And we have what's called shear pins. They're basically nylon screws, small 2-56 type screws that hold these 2 pieces together. And so that pressure will generate at least 30 pounds per square inch for each of the shear pins that it has to sever. And it'll blow this apart, and it'll pull this all out. And the tape on the Kevlar cord here, harness, will just snap instantly because that's not going to hold up to this charge. So the first charge goes right at apogee. The second charge is the backup computer, and it's watching for about 1.5 seconds to 2 seconds after apogee, and it'll blow as well. Now, if it's separated, the second charge is just blown out into space, out into the air. But for in case the first one didn't separate it, the second charge is a little bit bigger. We had an extra 25% on there to make it pop apart. Some people put a lot more in there, and they say either it's going to separate or it's going to blow up into pieces. And they're going to make sure that it opens up. So anyways, so it's falling now. So say this is up 6,000 feet, and it's falling down. and it's falling at about 30 miles an hour. And the flight computers are still monitoring the pressure, and it's trying to figure out when is it going to get down to like whatever I set the next chute to open up, which is usually around 1,000 feet, because these are very large chutes in here. We'll go down to about 1,000 feet. And then once again, we have two computers with two charges up in this section that will blow the nose cone off here. And at about 1,000 feet, what will happen is we'll blow this piece off here. It comes out and it pulls out the shock cord and the chute. So as you see, we got another blanket here that's heat resistant to protect the chute. And the chute will open up. This one here is a 5-foot chute, which will slow the rocket down to about 20 feet per second or less. I think this one gets us down to about 12 feet per second, to give you an idea. And that brings you back to the ground. Now inside the rocket, there's more, because you have more electronics than we ever had when I was a kid. And so inside there, we've got GPSs. Like here's one of the GPSs I've got. I could tie it onto the shock cord, and it's got a GPS chip and a transmitter that's talking to this guy here. And I can put in a speaker on here as well. This one's one of those home-built types. So it talks to me. So when the rocket was going up, this one here will actually talk to me and tell me its altitude, or how high up it's going, how fast it's going. It'll tell me when the drogue chute's been deployed, and it'll tell me again when the main chute deploys. Or if it goes into fail-safe mode, it'll tell me that news too, but most likely I already have seen that. But yeah, and then the GPS works as well. So it'll tell me where the rocket is. It'll give me the GPS coordinates, so I could plug that into my phone if I want, or I can switch over and it'll actually put a little arrow out, and it'll say, you're walking this direction, you need to go 10 degrees to the right, and it takes you right to the rocket. Now, the GPS only works for line of sight. So if it's a long distance off and it's gone over a hill and it's on the back side of a hill, the GPS transmitter can't talk to the little box that I got there. So what we have to do is this device here will record the last known location of the rocket. And what it'll do is it'll tell you to get to that location. So it'll guide me to that spot. And once I get to the top of that hill where it last saw it, it's usually close enough at that point. So once you hit the top of the mountain, it then syncs up again and guides you the rest of the way. So it lets you actually find it. And these types of things can get up to 10 miles. They can talk to each other. So up high, yeah, you got clear line of sight. It'll talk to you, and it'll allow you to actually know where it is. But as soon as it gets closer to the ground, that's when it gets behind things, and then you have problems. And you have to sort of walk to that point, and then it will sync up and tell you the rest of the way. And if it doesn't sync up at that point, you know that if it's drifted a couple miles when it lost, where it went over that hill and you walk to that hill, you know the rocket is continuing in that direction, so you just keep walking and eventually it'll sync up. So electronics is something that's new into the hobby that I got. And so this is the latest thing. I've yet to actually use it, but this is a camera. So this is a video camera that you can actually put on the side of the rocket, and it'll record. And what's really neat is it also has a microphone, so you can hear it. And I actually have a video here to show you one of these launches here. This is one of our club members, and he just activated his camera. So that's our launch site there. You can see the big open fields that we have. So there's Apogee, 5,000, over a mile up. And that's his small chute, the drogue chute. It went through the clouds so people can't see where it actually is. And this can get you some motion sickness here, so be careful. So right now, he's looking for his rocket. It's going to be up here a little bit. It's up in here. It's going to show up here shortly. Right there it is. So that's a rocket under the drogue. So it's falling back to the Earth here. The computer's operating and it's tracking its altitude, and now it hit the altitude for launching out its main chute. So that's the main chute that's popped open, and it slows way down. So that's probably 3/4 of a mile from where it was launched. Now, if you launch out west, like in salt flats and stuff like that, those rockets could catch wind and be dragged for miles after that point. We're not too far from the border, that's true, although we're not going quite that far. It'd be quite a distance, but yeah. So that's an example of a payload that we have in some of our rockets that we do. It's kind of fun. The university, so the site that we have is a very large site in the area, and there's a lot of area universities that have aeronautical engineering programs. And so those schools form teams, like a collegiate type team, and they actually come to our launch site to launch their rockets. So these teams are competing for scholarships and grants from like NASA, some of the big defense contractors, and because they're all trying to encourage people to develop these skills that are needed in the space industry. And so they're very much excited about the fact that we're going to the moon, that we might go to the Mars here. So they're all in that field trying to pick up that education. And one of the things they do is they join these teams and they come to our site to actually launch. So the student teams, which can be teams of like 25, 30 students, and they build a project to meet certain objectives. Like we had one rocket that dropped a drone out of the payload section, and then they would manually fly it back to their site, to where they were standing. We've had another one that had a steerable chute that it was still remote controlled, but their plans are to eventually make it totally autonomous. The idea that it could bring the rocket back to where the actual launch site was. So there's a variety of these types of challenges that are available to these teams, but they all have a schedule that they have to achieve certain milestones over time, and they come up to us to actually see. During the school year, we could have as many as 100 students out there all building their little projects, putting them together and launching them at the site. And they're rather spectacular because they're bigger rockets. They're up in the 70-pound range. And they're tall, maybe 12, sometimes taller. And they're flying on big motors. This one here that you saw here was an M motor, which is the largest motor we're allowed to launch on the field. So like I said, each letter doubles in power. Space shuttle, I once figured it out. It's something like a ZX or something like that. So if you keep doubling, it's a whole lot bigger than what we have. But there's some very interesting rockets that they actually launch. Plus, a lot of students go through a certification program too, where they want to get approval skills for launching rockets. So inside of our National Association, NAR, National Association of Rocketry, they have certification processes to determine whether you know enough about how to build and safely fly a rocket. And they're broken down to 3 levels: level 1, level 2, level 3. Level 1 is the first level. I mean, to do these low power rockets and even mid power, those don't require any type of certification. When you go to level 1, which would be like this rocket or the black one here, or even this guy here, that requires you to build a rocket safely. We help them install it onto the launch pad and they launch it. And if they're able to show that it went up successfully, came back when we inspect it for damage, if it's reflyable, we certify them for level 1 and they get their approval. Then they go to level 2, where they need to go to a more complicated rocket with dual deployment like I have with the drogue and the main. Anyways, at that level there, they also have to take a test. So they have to know all the rules associated with launching. And then they have to launch a rocket with a bigger motor in it and demonstrate that they can do that successfully, like at level 1. And if they do, they get to level 2. And that's where I'm at. I'm at a level 2 right now, certification. So I can buy bigger motors. Then at level 3, which is the biggest or the highest level, that's what I'm working towards. I've got my proposal that I've sent off, and I got a mentor now. That's a report that I wrote explaining what I'm going to do, what kind of rocket I'm going to build, how I'm going to reinforce it to make it handle the stress that's associated with the amount of forces that are going to be acted upon it, and how I'm going to make sure that it's going to be done successfully. Because when you get to level 3, you're starting to deal with rockets that are 50 pounds or heavier. So think about that. You're sending it up 10,000 feet. And if those chutes don't open, the rocket doesn't separate around. You got a 50-pound ballistic missile coming back into the ground. We call that lawn darting. We've had rockets that do that. But when they come into the ground, you know, something that's bigger than this even, they'll go 3 to 4 feet into the ground. And I'm not talking about soft ground here. I'm talking about packed ground. And then we talk about shovel recovery then, because you have to dig it out of the ground, and it's just a big accordion inside. It's a bad day for the Rocketeer. Although my wife does talk about the excitement of seeing a rocket go boom, but for Rocketeers, it's not fun. But yeah. So I'm working on my L3. I'm looking at probably the fall time period. I'm waiting for the parts to come in. I just got the motor recently. I got approval from the proposal, so now I'm just waiting for the parts to come in. I have to assemble it. I'll expand my report to include the development, the actual building of the rocket, because I have to document all the internal pieces to show how it's all being done. So you guys are welcome to see that. I've got several rockets up here for display purposes. So I'm thinking I can answer questions. You guys can come up here and look at these rockets. I've got some publications, like we've got Sport Rocketry. So if you want to see what's some of the literature that there is out there, or our Bible on model rocketry, and where they go. And one other thing I'll point out is the speed of these rockets. So this rocket here, I built to break the sound barrier. I wanted to go faster than sound, which is 760 miles an hour roughly. And so this rocket I built, and it went to, well, It went about 7,000 feet up and actually went low over Mach 1.04. But if I put the biggest motor that I can put into here, it would actually reach 1.4 Mach. So it's serious speed here and go up about 10,000 feet. So put a big enough motor in a small lightweight rocket, it's going to go high and fast. But anyways, at this point I'll answer questions. If you guys want to come up and see these rockets, they got little cards here that explain what all the cost of the rocket motors and the rocket kits themselves. You're welcome to look at that as well. Yes.
Certification.
Yes.
You said you had a National Rocket Association that does certification. Who certifies the certifier?
So we have to apply for that. So in our club, there's 3 members that are certified to give the tests to do certifications at level 1 and level 2. And I've got one of the 3, actually now it'd be 2 of the 3s can be done for level 3. So the way it works is one person who's already certified at a level higher than what the person is trying to get certified for. It only takes one person to certify the rocket. They know how to inspect it. There's a form to fill out and they review it. If the person is trying to be certified the same level as the witness of it, then you have to get 2 people at that level to review their rocket launch. And the people that can do the certification have to, one, be certified by the organization, and we send their name off to the National Association, so they empower us to do the certification locally for them.
Who empowers the National Association? Are you involved with, is this FAA or is this
No.
sir? Is this?
So when the Rocketry Association started off, the association wanted to maintain control of the whole hobby. And so they built the rules. They helped draft the rules for the FAA. So there's a set of rules or laws wherever we have to follow from the FAA, as well as the there's a fire FP. I forgot the name of the organization, but there's a fire protection, one that sets all the fire rules, and they also have rules about what you can do for class 1 and class 2 rockets. And we're a class 2 rocket. I'm good for these big ones. And then you get beyond the amateur level and you start getting towards the people that are, like SpaceX and so on, and they're even higher. And they got rules for all those. So what the National Association did is they set these rules up, and they basically police the organization to always follow these rules. The goal is to make it safe. So like, for example, there's about 2 million launches a year through the NAR. And out of those 2 million launches, they, over the last, since I think 1957, when they actually formed, they have not had a serious accident. Now, there are accidents that do occur. Biggest ones are usually just fires. So the NAR has insurance policy for each member and each club and the landowner who allows us to launch from. So we've got a $5 million insurance policy that covers personal injury as well as damage to personal property. And that's given to us as long as we're following the rules, we're covered by their insurance policy. So anyways, they set the rules, they got committees, they got boards that review anytime there's a failure. They ensure that you're using commercially. It has to be a commercial engine. So they verify that everything's safe about the whole process. And if something doesn't go right, they investigate and track records. So like maybe a manufacturer's got a bad lot of motors, they would then engage with the manufacturer to get to the bottom of what's the cause. It's sort of like the the transportation board. If the plane crashes, they got people out reviewing. We send in reports, and then they do investigations on that. Other questions?
Yeah, you might have said this, but the smaller rockets you buy as a kid in the hobby store, but the large ones, do you buy a kit for that too, or do you buy plans for it and then you build from those plans?
So you can go both ways. You can buy kits that have the basic airframe and then buy all the extra little pieces with it. Or you can buy all raw materials, like you could buy pieces of fiberglass pipe that's of a certain size, or you could build it out of like sonotubes, or some people build 12-inch diameter rockets out of sonotubes. The issue comes down to is cost. Like for my L2 or my L3 rocket I'm going to build, I had to make that decision whether I'm going to buy it as a kit or the pieces. The problem is with pieces, you end up having to buy from so many different sources that the shipping cost kills you. So you could save a few bucks on the materials, but you're going to pay a lot more on shipping. So most people go the route by buying a kit. So that's what I've done, is I bought a proven design, and then there's certain decisions I have to make along the way. If you look at my report, talking about how I'm putting in all the strength members, how we're attaching the fins, like for example, the fins on this type of rocket here, they're glued to the body of the tube. These fins here go through this outer layer of fiberglass into where the motor mount is inside, another tube inside, and it goes through, and then you put epoxy fillets on the inside of the tube at the top where the motor attaches, as well as where it attaches the lower tube, and then you put fillets here, this epoxy on the outside as well. So it's really locked in. So you have to come up with designs like that. Like I'll use some carbon fiber tape to actually reinforce the rocket to help deal with the stress that it's going to face. Yes, Frank.
Having been to one of your launches,
Okay.
do you want to talk about and find out about your launches and whether they know?
Sure. So this is the types of pads that we have out there at our launch site at St. Albans. We've got 6 low power pads, so anybody can come and launch. So if you guys have some low power things that are free, you can come out here. We have all the equipment to launch them. We do safety inspection on them first, but you're able to launch them. And then for the high power, if you got certification, you're allowed to bring those rackets out there and we can launch them as well. There's a small fee with high power. And then, as you can see, the distance here, the rails, they're actually further, the one on the right's high power, and they're further away from you based on how big of a motor you've got. So we can go up to 500 feet out from the launch site. So this is where we launch. We launch up in St. Albans. So St. Albans is about here. So this is out towards the water. It's a site, it's on Malcolm Road in St. Albans, and there's a 400-acre lot that we are allowed to launch from. We've got a waiver that allows us to shoot up almost 2 miles straight up, and we can support up to an M-class motor, which is a pretty big motor. There's all the way up through O I've seen that you can buy commercially at like 13,000 a pop. So we don't get those kind. We can't launch those kinds, but some of the bigger fields do. Our launch schedule is the 3rd weekend of every month. What we do on about Thursday before our launch, scheduled launch, like last week, we look at the weather for the weekend. And if the weather is bad, like the wind is too high, we cannot launch over 20 miles an hour. If the clouds are too low, like the clouds are down around 1,000 feet, it's no fun to launch a rocket because we can't shoot through a cloud. Or if the field conditions are bad, like it's I don't know, super muddy and flooded or whatever, we wouldn't hold a launch. So the 3rd weekend on Thursday, we make a decision as to whether or not we're going to do a launch that weekend, and if so, which day. We send it out to our mailing list. If for some reason that weekend's not good enough, we push it out a week and we try to reschedule. So last week did not fly because the weather was bad. So we're now looking at this weekend, and tonight we'll get together and decide whether or not to actually hold a launch this weekend. And we mail it out. So if you were to send me my contact information here or the club, if you send an email to them, we'll put you on the mailing list. So we'll let you know. There'll be an email that goes out a Thursday before every launch and tell you what the status is, whether we're having a launch or not. And if we're not, whether we're going to postpone it a week or not. So this would be the way for you to find out. So right now, this weekend could be a launch. Now, personally, I'm looking at the weather. Saturday does not look good. Clouds are real low and the wind is not too bad on Saturday. Fields could be muddy, but that wouldn't probably stop us. So, but the low clouds will. Sunday, it's going to be mostly clear skies. The wind's going to be higher though. Right now, different weather reports are saying different things. Some of them are saying it's going to be around 10 to 13 mile an hour winds with gusts up to 30. That 30 gusts are a little bit too much for us because we can't go over 20, but we can sometimes wait in between gusts to do a launch, keep your finger on the launch button and then launching between gusts. We do have little wind speed sensors that are there at the launch site so we can monitor the speed of the wind. But Sunday looks like the best of the 2 days. And we'll see how the weather goes. Like I said, we meet tonight and we'll make a decision. Other questions? Yes, Karen?
I have two questions. Do the segments ever separate when they shouldn't?
Yes.
And they rotate a lot. It looks like it spins.
Yes.
Is that an advantage or a disadvantage? Do you ever adjust the pins to slow that down?
You mean when it's going up or when it's coming down?
When it was going up, I guess both.
So some people do it on purpose. They'll canter the motors, like they'll have dual motors and cause them to do a curlicue as they go up. They could also do something with the fins. Typically, no one does that because it's harder and it's less predictable what's going to happen. But some of the more experienced Rocketeers will do something like that. If it starts end over end type somersault, that's when the electronics usually kicks in and jettisons all the parachutes. What was the other question?
Do they separate?
Oh, yes, they do. And I've had it happen on this rocket here as well, that there's a charge that pulls off, separates from here to the upper part of the rocket to get the drogue chute out. And if I've miscalculated the size of the charge, and you're supposed to do ground tests beforehand so you know what works and what doesn't work. Then here, mine broke both pieces apart because the force at which this piece separated and then it hit the end of the shock cord, and that force was enough to cause the nose cone to pop off as well, break its shear pins. So I had both chutes out immediately at the high altitude, which meant I had a long fall. So that was not a bad thing. But when you get these high-powered rockets, you can have problems where fins break off. That's one thing that can happen. They call a fin flutter. So they start shaking. If you break the sound barrier, there's more forces on the rocket. There's like a bow wave that comes down and comes back at the rocket. And so it creates a lot more stress as well. So that's another thing that can cause something to fail, is that kind of stress. But yeah, it does happen. It doesn't happen all the time, but it does happen. Let's try to keep it as rare as possible because, my rocket, at this one here, I haven't paid for paint on it yet, but it's probably $750 $750 is what I spent in it. My level 3 rocket that I'm building with the motor and all, I'm looking at a little over $2,000 for that rocket. And my wife, of course, is.
That was kind of stealth.
Yes. Oh, yeah. Actually, you keep tracking comments about all these spend. But yeah, I had to buy 3 motors. So I got some test flights I'm going to do with it. So that was about $1,000 there, a little less than $1,000 just for the motors. And then the rocket itself is like $750, plus I had to buy another $200 worth of hardware. I'm gonna probably put paint on it, so I'm probably gonna go automotive paints and spray it on. So that's gonna add a couple $100 as well. So it's expensive.
See pictures of your kids, those are your kids?
No, none of my kids came up here. I did them down in Virginia. I took them, or I actually did a launch from a school. But yeah, these are kids that come out to our site. So we do get kids out there. We sell these little saucer kits. They're basically a paper plate that we put a motor in. And it's $5. So if you brought some kids out there and they want to really launch their own, you give them a paper plate, tell them to put their name on it and color it however they want. And they can have all that fun. And then we glue the motor in and put it on the pad for them. Then we let them actually push the button to launch it. So it goes up 100, 200 feet, something like that. But it's exciting for them. We do that at the local schools as well. Yes. Any other questions? Yes, in the back.
Do you always point them directly straight up, or do you ever angle them to compensate for wind or anything?
So we do angle sometimes. It depends on the wind speed. We're prohibited to go more. It has to be nearly vertical. There's a slight canter that we can put in there, and you can aim them into the wind. That helps because you shoot them into the wind, and then the wind blows them back towards you. The other part is these rockets, especially something like this here, there's stability issues with the rocket. It's actually, this one's overstable. So from a engineering standpoint, there's 2 points on this rocket that you need to know. One is center of pressure. So in other words, what's the drag on the back of the rocket? So these fins create pressure and pull on the rocket. So there's a center of pressure. So that means that if I were to tie a string about here, and I were to spin it around in a circle with a wind or in a wind tunnel or something like that, it'll balance about here. And then there's center of gravity, which is right about here. And so center of gravity, where it balances, has to be ahead of where center pressure is. And the rule is you want it to be the diameter, at least 1 diameter ahead. So this one here is 4 or 5 diameters. We call it overstable. And it's a problem when it's windy out. So when this is going into, so if the wind's coming from the back of the room here this way, the rocket will start to angle into the wind because it catches the fins and it'll start pointing into the wind, which could be an advantage because then when it deploys its chute, it's coming back your way. So it cuts down the walk, but you lose altitude when that happens. Other questions? Or you guys want to come up here and see some of these rockets posts? They're designed to go up, 10,000 feet. You come crashing back down to the ground at pretty high rates. So they should be able to handle it. But if you want to touch one, just be careful. Okay. Thanks, everyone.